Hello and welcome to today's IWCS webinar. My name is Connie and I'll be your WebEx producer for today's event. Now I'm pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to place a question anonymously and during the presentation. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Ethan Bremer, developmental chemist at SACO AEI Polymers in Wisconsin, USA, who will be presenting his paper on low smoke, zero halogen compound considerations for copper and fiber optic communication cables. Ethan Bremer is a developmental chemist for SACO AEI based in Sheboygan, Wisconsin, USA. Ethan has over 3 years of experience in formulating and developing halogen-free compounds for power and data cables. Ethan received his bachelor's degree in chemistry from the University of Wisconsin, Platteville. Ethan, we welcome you to present at today's IWCS webinar series event.
All right. Thanks, Ed. Thanks, Connie. As I said, I'm Ethan Bremer. I work for SACO AEI Polymers. And before we jump in completely, I'd like to thank you all for coming in this kind of odd time we're living in. There's a couple people as well alongside me that work at SACO that need a little bit of recommendation and appreciation. Caleb Bro, who's also a development chemist, scientist, and then there's Darren Collette, who works in our UK facility, who's also helped greatly. One person not on this is Travis Getze. He no longer works for SACO, but deserves appreciation as he helped us develop this presentation and data set. So the low smoke, zero hal compound considerations for copper and fiber optic communications cable presentation really drives home a couple points that throughout the development process of new compounds for fiber optic, we can do several things to mimic and predict how these things are going to behave under fire conditions. However, it's not always easy throughout the expanse of a life cycle to know exactly how it's going to perform. So this is kind of just a map of the areas that SACO will source and help you with. So we have a global presence, and questions and formulations for really any market can be found throughout our portfolio. But for this purpose, let's jump into the fire safety side of things. The biggest harmonized standard set that we're targeting today is the EN 50575, which is CPR out of the European market. So it's generally a global endeavor. There's multiple people targeting this standard set for their end products. The United States also has a set of flame testing that is very useful, but the 50575 set really is the most important. So I guess for a little bit of background, in North America, the halogenated systems are widely known as the best way to achieve a high fire performance. Globally, the low smoke, zero hal, halogen-free fire retardant solutions are becoming more widely used. This is generally due to the Grenfell Tower fires, things like King's Cross fires, where halogens may not have been deemed as safe, and it's important that we keep pushing in the direction where we don't have a halogenated system. So that being said, the new materials for low smoke, zero hal, as they are very fire resistant, they're not generally considered as fire resistant as halogen materials. So that means formulating for the North American market can be a little bit dicey at times as you're competing against some of the things like PVC and the brominated antimony synergist sets. But you'll say the market is growing considerably. And a lot of that has to do with 5G. And please do not believe the rumors that 5G is in any way related to coronavirus. I don't want to have to address that. But as we roll out more 5G networking, the density of the fiber and the amount of fiber is going to increase drastically as we put in these nodes to attain high capacity, high data rates, all of this in a very dense area. So that means that there's going to be a lot of cable being put in, and frankly, a lot of new material is going to be needed to address safety concerns. So the large-scale testing for these materials, like CPR, FT4, FT6, plenum is not really for this style of material, but still relevant in the future, can lead to some high costs for manufacturing companies as well as companies like SACO that are developing these materials. Most of the cost that is derived from all of these materials is from generally the scale of process. So in the lab level, you can do testing on a very small sample, and it really costs a very negligible amount. But the second that you want to know exactly how it will perform on a specific cable for construction and in a certain test, that generally drives the cost up, as well as the timeline. So it's something that wants and needs a new process to get rapid development at a lower cost. So with this presentation, we're going to focus a little bit more on some intermediate lab scale methods, not the UL-1666 and the other large CPR scale testing that just isn't cost effective for a large variety of formulations. Once you get down to one or two, yes, that's definitely the way, and in no way can it be replaced by these VW1s, FT2s, the small scale testing, but there has to be a screening method. So let's take a look generally at some of the more harder to hit requirements that are specified in UL-444. So fire performance is the focus of this, but everything also needs its physical properties. So tensile strength, elongation, aging, cold bend, LTB, oil resistance, and weatherability. So this is just an example of when I'm in the lab formulating what I'm looking to hit. There's a couple reasons why, for example, the tensile strength is 400 above the UL-444 requirement. That's so that you can cross it over into other specifications outside of fiber optic. But it's still good to have that headroom that you know that a compound will be able to meet all of these specifications. And in case something does go a little bit wrong, you're not living on the teeter-totter edge. Especially in the lab, SACO isn't the only company that uses mixed bowls, small extruders that don't always scale the greatest to a full-size manufacturing material. There always is going to be a little difference. It's just tuning in exactly how you can circumvent the large shifts in data. So it's important to have that headroom while you develop. We really won't touch much on this other than some of the formulation effects in the future, because this will be primarily focused on the fire performance. So let's touch a little bit on UL-444, as it is the guiding specification for communications cabling, not necessarily always fiber optic, but for comm cable, it really is important in USA, and it does overlap with a couple of other specs like UL-1277 for tray cabling. So low smoke, zero hal solutions over the past have been comprised of high levels of filler, and those fillers are primarily hydrated fillers, ATH, mag hydroxide, there's brucite, ground grades, all of that. It's really good, but it also inhibits some of the physical properties above, and to get higher levels, you need to find some either synergistic minerals or some other ways to just meet char, things like char, etc. We'll cover a little more later. So this will focus on the thermoplastic compounds, UL-1666, CPR B2ca cabling construction does make a pretty big difference. So I will be telling you a lot about what we've done, the tests we've done at the lab, but at the end of the day, the construction on the final cable can make or break the the lab results that we have found. So we could have something that is the greatest new flame retardant material on the market, but if it is decided to be put on a construction that has a high amount of flammable content underneath a jacket, it may not matter, depending on how the construction thickness and all that plays into it. So I guess what I'm saying is we will do everything we can in our power to make sure you have a very good flame retardant material, but there are ways that can be sacrificed later down the process. So let's take a look really at what the breakdown is on some of these tests and what it really means for cable ratings. So think of this table as really broken down by type of test and then how it corresponds. So on the far right is B2ca, which is comprised really of two main flame tests, the EN50399 and the 60332-1-2. There's some other branches amongst that. So this is primarily what I'm going to be speaking to throughout this presentation. So when I say fire size, that generally means the output, the kilowatts, the amount of power, the raw power thrown by a flame, a burner, whether it's ribbon or a single Bunsen burner. These are also ranked if you take the VW1 and go to the left in severity. So there will be another slide that covers that a little bit. The CPR specs are on their own. The 60332 versus 5399 are also in a similar fashion, but it's not the same. So we can come back to that slide if anyone needs to in the future in the Q&A, but just remember that 1666 and the 50399 often are considered very similar, but in all reality, this actually uses a calorimetric equation, while the 1666 uses thermocouples for smoke or temperature gradients. CPR classes, this is generally how it's broken down. There's additional criteria as well, which comes down to smoke acidity and flaming droplets, which in their own right are very difficult to meet for even low smoke zero hal compounds. You'd think to yourself, why is acidity a problem for some of these? It just can be. They're very pickled. So, as I was saying, there really are two worlds that we live in. There's the small scale, which is comprised of the EN60332, VW1, FT2, which are really burner-based tests. I believe the EN60332 uses propane instead of the methane, so it is very important that we rank it a little bit higher as the calorimetric off-gas from that, or not off-gas, but the quantity of energy is a little bit higher. On the right is the large scale, the things that we can't really do in the lab without making cable and really trying to meet some of the full progression testing requirements. So that being said, there has to be some middle ground to verify that what we are making is consistent with the large scale. So that's where modified testing and calorimetry come into play. As we progress through this study, we're going to need to understand a few things because there's going to be a large data set revolving around 6 samples. So we have a classic MDH style formulation, well, 2 of them actually, which just vary a bit based on the MDH load. The resin generally is EVA blends, but it is the same level of EVA. ATH, we have one of those just to drive home a point that ATH doesn't always perform quite as well as MDH, but there's a cost benefit. And then there's also a proprietary list of samples which SACO has come up with in the past few years just to show the advancements that we've made. Not all the data sets are complete, and that is just based around the innovation path that we choose. So if you look on the right, one more final piece that might be interesting for people that aren't quite as familiar with the industry. This is what I view as a classic system. EVA, LLDPE, coupling agent, and MDH, and then a little bit of antioxidant to balance out and make sure that you're not degrading your polymer. So for those that aren't as familiar, coupling agent is probably the only thing that really is a little more questionable. Think of it as when we put in these filled hydroxylated metals, they don't really blend. It's oil and water. Coupling agents make sure that the LDP and the EVA play a little better with the MDH. They blend, they don't reduce the physical properties, they kind of just mesh better together. So, the first thing people think of when we dive into research and study of new formulations is LOI. And it's really for a good reason. It's fast and it's easy, it doesn't require a lot of construction, it's overall cheap. The largest issue with LOI is if you remember back to the days when you were sitting in your classroom and the fireman was telling you, all right, this the heat triangle, oxygen, fuel, heat, you need all three, take one away and it won't work. Well, LOI only focuses really on the oxygen source. Heat is consistent and the fuel is generally consistent. So it's a little bit skewed. So if we just look at this slide, you would think, wow, Classic 2 has really, really good fire performance. We should go forward with that. We'll use that for a new B2ca certified cable. Well, in all reality, if you look at the VW1 results, the propagated flame testing, it doesn't always play out that way. If you were to expect that LOI was going to be indicative, you would think that this VW1 point would jump up and then it would drop. It would really just be continuously following this at a slightly higher level. That's not what we see. Obviously, with some of the new proprietary materials, the VW1 burn time is significantly lower, even though the LOI is not as stellar as the 40 that's displayed as the Classic 2. So it just kind of points out that there are some flaws in LOI, and that can lead to some false conclusions. So you just have to be careful. A lot of this comes down to the actual propagation mechanism that is behind the VW1 test. So if you were to hold a candle from the bottom, it's easy, right? You're not burning your hand. But if you were to move the same distance up above the candle's flame, you'd burn your hand. It's the same concept in a wire. You get the burn at the bottom, propagates up, heat, the little radicals essentially continuously attack the plastic as it goes up. It can also lead to some candle wicking effect, is what it's often called, I guess. So, TGA is a supplementary technique. Often not really thought of. It's a little bit tricky because you can cheat this as well with using non-combustible materials, inorganics that stay behind. But it also, that method has its drawbacks. You would see it in LOI. So, if you look at the TGA chart, I can't display the full thing because people that are very gifted can understand exactly a formulation head to toe by looking at a TGA. But mass remaining is very important. Think of TGA as being able to tell you, all right, we've burned this cable, how much will remain on that cable if it's formulated to resist the forces of gravity and laminar flow from heat. But it's a good indication of fire performance in its own right, as you see in the proprietary materials, which also had the really low VW1 burn time. It's just, think of more thermal insulation than you would get if you had less material on the cable or wire. So VW1 is something that's always been a little iffy for passing for low smoke zero halogens, but the proprietary methods correlate quite well with TGA on their passing in a VW1 testing. Okay, so here you go. This is a little more in line with what you would expect. They're completely inverse. So high amounts of VW1 burn time mean there's generally not as much mass remaining from the TGA. Actually, I should elaborate a little bit before I move on to the next slide. When we do TGA, unless we are looking for something very specific under oxidative conditions, we generally use nitrogen until 600 degrees Celsius, and then you switch to oxygen to burn off any additional carbaceous layers. The purpose for this is, under nitrogen, it's a much smoother transition between materials that evolve gases. So you get a very consistent thermogram every time you run it under nitrogen compared to oxygen, which oxidative effects can be a little tricky. All right, Connie, can you help me out on this one a little bit? Get the video running. So something we've done recently, which isn't entirely our own idea, is a UL-94 style testing. Modified is what we're calling it. So it consists of 8 10-second applications with a 10-second spacing in between each of the burns. You don't wait for the combustion to stop. In fact, if you do, generally some of the higher flame retardant materials behave significantly more. So it's hard to tell the difference between them. But Connie, can you just play that one more time so I can get back to talking to it? You can see in this video the role that the formulation actually plays. These are the exact same thickness. The proprietary materials hardly burn up. They char along the edges. You don't wick up the sides. It's an effect of both the TGA that we saw as well as some of the actual flame retardant properties that we'll see in cone calorimetry in the future. But really what you're looking at is a relatively successful UL-94, well, modified UL-94 burn compared to what you're seeing now, which is the classic material. That's the higher filled, just MDH, EVA, LDP, and a coupler. So really what that's showing is once you put that on a wire, it's capable of high levels of flame performance all on its own. And that is a very important piece to take away from the lab. If we can't verify that the material is flame retardant on its own compared to what we've done in the past, then it really is a bit of a moot point. So it's difficult to transition to the next level of lab testing. So there are other companies that use UL-94 style testing. It's a little different than what we've shown here. They'll vary the thickness of the bar. So it'll still be 125 millimeters. It'll still be 13 millimeters in its width, but the 3 millimeters will be the piece that they vary. We've done this as well. We've just found that it's easier to use a 3 millimeter, or for the proprietary materials, you can go to 1 millimeter. The thinner you go, the easier, or I should say the harder it is to pass the test. Thin layers tend to burn better. The oxygen content versus fuel is very important. So with that being said, coupling the UL-94 with cone calorimetry can be some of the best data that you can get to decide if a material is worth progressing with. So cone calorimetry really tests all sides of the combustion triangle. It has something called a paramagnetic oxygen detector, which shows the oxygen consumption of the combustion. It also has a controlled heat flux as well as monitors thermocouples in the exhaust, and it has a scale that will show you mass loss. There's also some very expensive and wonderful other pieces that they've recently added on to new cone technologies, such as IR detectors and various other calorimetric quantitations. So it's becoming better than it was, but it still can be cheated, as every test can based on the formulation. So this is the part where I get to tell you ATH and MDH are not equivalent by mass. So that is one of the hardest drawbacks in the current industry. ATH is cheaper. That's the aluminum hydroxide versus the mag hydroxide. ATH degrades into 3 waters and some alumina, but it only gives off around 1,100 joules per gram. While MDH, while it only gives 1 molar H2O, it does 1,200 joules per gram. Yep, that is the correct value. So that is really important because the flame retardant mechanism behind these materials for low smoke zero hal really comes down to the twofold. One is the amount of char it leaves behind. That's the magnesium oxide and the aluminum oxide, but also the endothermic reaction that occurs. So ATH really just doesn't pull out as much energy to degrade as MDH does. So it's kind of important to understand that while MDH is the top of the line material we currently use, it always is fought with ATH, but ATH just cannot hold as much ground. So a battle between exotherm and endotherm occur when we're doing low smoke zero hal, and that's why it has to have such a high level of load of the MDH and ATH. So, let's see, can I go to the next? There we go. Most materials for cone calorimetry are going to have the same amount of energy when they burn with respect to oxygen. So that's 13.1 megajoules per kilogram. That is the core concept behind cone calorimetry. Unfortunately, you never see 1 kilogram of oxygen in a burn. That's just not how the world is set up. So someone very smart in the lab once did the work to understand the calorimetric effects of the oxidative degradation of a vast number of materials. So how this cone really works is when you burn something, it spits the gas out into this piping system, goes through thermocouples, the paramagnetic oxygen detector, gets all of these values. But what it really is doing is determining, all right, at the start when there's no fire, how much oxygen is in this cylinder. All right, there's combustion. All right, we're going to remove X amount of oxygen, turn it into carbon monoxide, carbon dioxide, and it'll reduce that oxygen concentration. So once you start the test, it'll begin to determine, all right, how much oxygen is left in this cylinder. And that is the basis of the calorimetric conversions. So with ATH and MDH, you have a slight adjustment as O2 gas density and temperature factor change. This is just early chemistry laws. So you have to remember to adjust a little bit as we go. So now that you understand a little bit more about how cone does its testing, you can actually see it in real live data. Here, this was some of the proprietary data that we collected a couple of years ago. If you really just look and were to flip over this oxygen concentration versus time, it aligns almost exactly with the heat release versus time. That is exactly what we saw above, where the calculation is reliant very heavily on oxygen concentration. So in a way, it's similar to LOI if you want to think of it that way. There's just a lot more happening as you go around with this testing style. So it'll also provide you the caloric content, ignition time, peak heat release rate, which does come out in some of these larger scale tests, the EN50399 specifically, and the temperature for UL-1666, which is related to the peak heat release rate. Maybe not as directly as some would like, but it's indicative to say the least. So similar to LOI, it doesn't always predict the flame performance of a cable. This is where char, unfortunately, comes in. As you build a layer of intumescent or non-intumescent char in organic, it slows down the rate at which volatiles can be accessed by the heat. So in a classic system, you're not going to have that problem. The oxygen content is always going to be there. You're going to have consistent combustion. Cone calorimetry falls short when you have a material that is highly effective at insulating thermal materials. So keep that in the back of your mind. Cone is very good, but it does still have its flaws. One of the more useful tools that does come out of cone, however, is the smoke density system. It's an IR laser. Beer-Lambert's law, essentially. As there's more smoke, the amount of laser you would see on the other side decreases. So think of it that way. But you need that to predict how the smoke density effects will come from CPR, FT4, and FT6. This is just an example of some cone data which you would standardly see and what you should expect if someone is to provide you with cone data on a compound. You'll want to know what the peak heat release rate is. The time to ignition, lower is better for both of those. Average mass loss is good to know because it does relate to the amount of material that you are charring. Total heat release rate is more of a overall look versus mass. So, and then effective heat of combustion and caloric contents are the middle ground, I guess, where you get both information by mass as well as the caloric content of the material. So good screening tool, but definitely needs to be paired with the other tests that we provided above to bridge that gap from small scale fire testing to the large scale. So lastly, I guess we can look a little bit more at some of the results from the EN series of testing. and just show that, yes, with the tests that we saw above, you can drive some of the proprietary compounds versus the classics in the right direction, and that we are slowly, as we evolve to new forms of technology, making some of these tests not as linear in comparison. So TGA and LOI don't always equate to the exact same levels of flame performance as they previously did from systems that were similar. So you can't always just say, well, historically we saw this, it means that we'll get a pass. Not really always the case. So, and just a reminder again, cable construction does have a large impact on how these materials will perform. We'll work with you guys to get you the best material we can. More than willing to tweak it. Every company will have to do that at some point, and it's really just a more of a partnership to think of. So lastly, this is some of the breakdowns on the acid gas and smoke density. Important to know, again, cone calorimetry is useful. Acid gas is in its own realm. If you have FTIR sensor for cone, you can point it in the right direction, but overall, it's kind of hard to predict. Mass table, just to review again, now that we've covered all of the outputs that you get from these testings, how they kind of feed into the flame testing styles that we've got for our major cable designs. So slowly transition, this way is hardest. So keep that in mind. This is what I'm proposing. You just kind of work your way up, and as you develop a material, try modified UL-94, VW1, and then pair it with cone calorimetry, LOI, TGA, etc. The last piece of information that you really need to know while you're tweaking formulations, while I'm tweaking formulations, everything has its drawbacks. So if I'm going to drop the caloric content of a material, I want to add more ETH, MDH, okay, whatever. That's going to decrease the elongation. It can make the material a little stiffer, and the tensile strength could increase. But there is no gain without a loss somewhere. If you want to boost the LOI, oftentimes EVA is the answer, and by doing that, you lose some of the low temp properties. Keep that kind of thing in mind. When we tweak a material, there's always going to be some form of drawback. It's our job to bring that to you as quick as we can, and we should have the knowledge to tell you what the change will do. So in conclusion, we're going to see increased volumes. There's going to be new materials that we're going to need to meet some of the more stringent requirements. There are still gaps going from the lab scale material all the way up to a finished cable. So as a community, we need to keep driving new intermediate test methods and trying to get a more linear prediction on how we can develop materials. But we also have these methods that I went over. When paired together, can give us a relatively good idea. So let's keep driving the cost down on some of these development methods using all of these smaller scale techniques, and get you guys some new compounds. So with that, thanks everybody for listening. I guess I can give you my presenter's information. Feel free to contact me. Let's do some QA.
Thank you, Ethan. At this time, we will ask as many questions from the attendees as time permits, starting with this first question. For copper conductor cables, I assume the polymer jacket is the major contributor to smoke and toxicity. However, for single conductor FTTH or ADDS fiber optics, how much is contributed by other components, such as polymer fiber tensile reinforcement, ripcord, etc.?
Yes. So that is always a factor. A lot of times when you're using constructions, the purpose of the jacket really is to thermally protect and provide safety to the inners, which are quite a bit more conductive or capable of combustion. So it really does depend on the construction, but generally, yes, some of the inners can cause failures. So I mean, we can expand on that more if you have questions on specific parts of the construction, but I guess I'll leave it there. Yes, it's always a concern.
Okay, thank you, Ethan. Next, have you compared low smoke zero hal materials to low smoke halogenated PVC materials used in plenum rated cable jacketing? And if so, how does flame spread or smoke generation compare on cables?
All right, yeah. We haven't directly, to the best of my knowledge, compared to a plenum-rated PVC. Very well aware of what it can do. Plenum is a really touchy subject for low smoke zero hal. There's really nothing out there that is truly halogen-free that's capable of dealing with a plenum in a polyolefin system. So that being said, it's something I would love to address in the future, but right now the technology platform just isn't there.
Thank you. Next, are there lab-scale fire test methods that accurately and repeatedly predict full-scale cable testing, such as EN60332 3C or UL-1666 riser, etc.?
To the best of our knowledge, there is not a small-scale lab test that adequately predicts exactly. Okay, let's. I guess I should break it down a little more. You have the exact same cable construction, and you're doing a test on a small lab scale versus a large fire testing like the 1666 or 50399. There really isn't a way to say this data point exactly predicts that we will pass on the large scale. So unfortunately, that is not the case.
Okay, thank you. Next, why are the tensile strength requirements in UL-444 only 1,200 PSI for low smoke zero hal when halogenated materials are 2,500 PSI minimum?
That is a really good question. I'm not sure if I can answer that. I would suspect a lot of it has to do with the loading that you historically use, but it's a good question for UL, I guess. Sorry, I can't answer that one. Okay,
thank you. Next, did you compare low smoke PVC compounds to low smoke zero hal compounds in the cone calorimeter? How did they compare?
We have not done low smoke PVC in our cone calorimeter. It's not something our company really deals with. We have other brominated materials for building wire that are halogenated and using antimony synergists, so it's kind of similar, but not really. Generally, the halogenated materials are relatively close, but not always the same. It depends on the system, VW1, FT2, what style of UL-44 we're using. But yeah, it's a different flame retardant mechanism too, so it's hard to compare them exactly. Think of the halogenated systems as a gas phase mechanism, while a lot of the source for the flame retardancy from these low smoke zero hals is originated in the actual solid phase, so forming char, that endothermic reaction. But no, I don't have data I can show you on the PVC side of things, but can on a brominated system.
Okay, thank you. Next, is acid gas generation a required test for CPR fire classification, or is it optional?
Okay, so it depends on the class that you are looking for, but generally you will need it depending on your application. So it's always smart to have it in the back pocket and check with where they're installing the material. But the 90% is, I would say, required, yes.
Okay, next. Would you perform the modified UL-94 and cone combination for wire in U.S. market standards?
No, I don't think I would. The reason being, I believe that in the standards you need to be as close as you physically can to the material that you are going to sell, or not the material, but the final construction you're going to sell, to be very, very certain. I guess it's almost a legality thing where you should have it certified on the construction that you're really looking to sell. So definitely an indicator, but I would not use it as the final say in a standard.
Okay. Next, will 5G require non-HAL materials only, or are there applications where HAL is required for 5G?
It's not something I've dug into a lot, but if you think of it based on the requirements for the cable, it will depend on location primarily. So anything that's CPR rated, and if it's required by the installer, then it will be halogen free by nature. If they're requiring just an FT4, there are ways around it. So I guess that's more of a question for a cable manufacturer than me, but we just haven't breached that gap yet.
Okay. The next question I'm going to ask, let me know if it's complete enough. The next question simply says, what is the grade? Subsequently, the person asked, what is the difference between TP521 and this grade?
This grade. I suspect that they mean the proprietary materials that we're using. Think of it as a new technology platform. There's some new materials that are non-resin based in the system that help with the fire performance. So that proprietary 1, 2, and 3 really have a couple ingredients that just aren't in the 521. Hopefully that answers it. If not, just let me know.
Yes. Okay. Next question. Since low smoke zero hal and HFFR are not standard-based designations, what criteria test do you use to consider or qualify a raw insulation or jacket compound as low smoke zero hal or HFFR?
So there are a couple different tests. There's the NES 711. There's the ratings for the acid gas. Generally, those are what you push towards when you're looking for a non-halogenated material. The halogen really forms an acid in these tests and will give it away that you're using anything halogenated. So that's maybe not the answer that you're looking for, but it's the best that we currently do to push towards a non-hal.
Okay, thank you. What is the tear resistance level? Is it crack resistance to work in high ambient temperatures like 55C?
Tear resistance or crack resistance? There are two different tests in my mind as a formulator. So let's follow up on that question after this, and we can go through some of the standards and figure out what exactly you're looking for in the question.
Great, great. So that'll be taken up offline.
Yep.
Next question. While selection low smoke zero hal for cable jacketing, what are the most important parameters to consider for LOI or TGA or what else?
Okay, so when you're looking for, is this a formulation question? Could you just repeat the question? Sorry.
Sure. While selecting low smoke zero hal for cable jacketing, what are the most important parameters to consider regarding LOI or TGA or others?
Got it. Okay, so when you're selecting a material, really you have to look at a combination and think of what you need for a test. So if you're, for example, looking for a material that will perform well in service emergency cablings, you're going to want something that chars really well, right? It has a high amount of TGA mass remaining after the burn. The LOI isn't as important. But if you're looking for a high fire retardant material to pass some of the caloric content tests like the UL-1666 or B2ca for CPR, you want a material that has a little bit higher LOI, also has the char, and has things that are really good in the vertical propagation. So I would say the VW1 and the modified UL-94 are probably the most important examples of what's going to provide you a solid ground to work with.
Okay, great, Ethan. At this point, based on time, we need to move on and conclude. However, I will remind attendees that certain questions we have not been able to address will be taken up by the presenter. So you will get a response to your questions subsequent to this. I'd like to thank you, Ethan, for presenting this very interesting and important topic today. Please note the contact points being shown here should you wish to contact Ethan after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, May 15th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 68 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader, showcasing new technologies in cable and connectivity products, processes, and applications. Our next 69th Annual International Conference will take place on Sunday, October 11th through Wednesday, October 14th, 2020 at the Rhode Island Convention Center in Providence, Rhode Island, USA. Also, the next UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 23rd through Thursday, March 25th, 2021 at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.